So yes, my name is Nicholas, and I'm going to be talking about our paper, Hidden Voice Commands. This is joint work with my co-authors, Pratyush, Tavish, Yuankai, Micah, Clay, David, and Wenchao. So a little bit of background before I get started. So devices have increasingly been using voice recognition as one of their primary modes of interaction. So we have phones, tablets, smartwatches now use speech recognition, and other devices whose basically their only mode of interaction is through speech recognition with the Amazon Echo. Now, speech recognition opens up new possibilities for attacks. Because the voice channel is unauthenticated, it's possible for me to give your device a command, and your device won't actually know that it's me who gave it the action. The device has no notion of who it is, who their owner is. So today, you can imagine that it would be very easy for me to walk up to your device, and if it's listening for speech recognition, say, okay, please text some premium SMS number, and your device would take this action. Now, of course, it has to be listening for commands, but if it is, this is something that I could do today. In a future not too far from now, you can imagine that you could walk up to someone else's device and say, okay, please pay someone else $100. And we are actually seeing that this sort of feature is going to be implemented. Apple has said that Siri's API is going to be released to third-party developers, and payment providers have actually said that they want to allow this for convenience. So this is a potential serious problem in the near future. So what we're going to do is we're going to show you that we can actually make these commands stealthy, so it's hard for a user to understand what is actually being said when their device is controlled. One of the primary reasons why this attack is not terribly appealing today is that if I walk up to you and command your device, you'll be aware that your device was commanded and can probably try and undo the action, and also will be able to confront me having just made this action with your device. Specifically, what we're going to do is we're going to produce audio which sounds like noise to humans, but sounds like speech to devices. So this is audio which, when you hear it, is just going to sound like something that's a random noise, but when your device hears it, is going to actually recognize as some particular type of command. And you should think of this generally in the problem of space of attacks on machine learning. So speech recognition is just a machine learning task, and what we're going to do is we're going to produce some audio which in reality should have the class of non-speech, but the machine learning algorithm is going to classify it as speech, and even more, it's going to classify it as a given phrase that we want it to hear. So before I actually start talking about how the attacks work, I need to give you a little bit of background on how speech recognition works. So speech recognition basically is a machine learning problem. So we start with some audio, we feed this into a machine learning algorithm, and feed that, and it gives us output text. Now, of course, it's not actually this simple because the input space is very, very high dimensional. So audio is sampled at something like 44,000 times per second. If we have 5 seconds of audio, there's 250,000 features. And machine learning does not really handle this very well when mapping only down to a couple of words. So what we do is we split this in half, and we split this into two pieces of a feature extractor and then a machine learning algorithm. So the idea of the feature extractor is we're going to try and reduce the dimensionality of the input from something very high dimensional to something very small dimensional, and then we're going to take those small dimensional feature vectors and feed those through this machine learning algorithm to give us the output text. Now, there are lots of choices of what machine learning algorithm we want to use. Traditionally, this was a hidden Markov model used almost exclusively, but more recently, people have begun using recurrent neural networks in order to give slightly better results. Our attacks are basically agnostic to the machine learning algorithm that's being used, so I'm not really going to discuss that further. What we need to talk about a little bit more is how the feature extraction works, because that's what's different in this domain. So for feature extraction, we start out with some really long input signal. And what we're going to do is we're going to split this into a series of overlapping frames. So we're going to split this to be the first frame, second frame, third frame. And now, for each frame, we're going to call a function which is called the MFC on each of these frames to give us the feature vector. The MFC you can think of basically as the Fourier transform plus some additional stuff to reduce the dimensionality a little bit further. Basically, we're transitioning into the frequency space and then doing a little bit of processing on the frequency space. So we do this for each of the frames to give us the feature vectors x0, x1, x2, and then these feature vectors, again, are fed into the machine learning algorithm, and then from there, we get the text. Okay, so that's the background that I need to give in order to explain how our attacks are going to work. So the first attack I'm going to present is a whitebox attack, where we assume complete knowledge of the system, the model, and everything else we might need to know in order to attack it. So if you recall that how the processing works with recognition is we start on the left and work our way towards the right to get the output phrase we want to hear. What we're going to do for our attack, since we have complete knowledge of everything, is we're going to start from the right with the text that we want the device to hear and sort of work our way backwards. So we start with this text, and we run it backwards through the machine learning algorithm to find some feature vectors, so that if we could hit those feature vectors, when run forwards through the machine learning algorithm, it would produce the text that we want to hear. We then take those feature vectors and run those backwards through the feature extractor, and this gives us some audio, so that if we could produce this audio, it would give us the correct feature vectors, which again are going to give us the correct output classification of the text. So in order to do this, I need to be able to convince you that we can invert both the machine learning algorithm and that we can invert the feature extractor. Now, it turns out that previous work has covered the machine learning algorithm part for us. If you're familiar with the work on image recognition, it's been shown that it's very straightforward to produce images which look like anything you might want, but have a very strong classification as any image you might want, for example, a school bus. This is all done, and we sort of take that work. What's different in our space is the feature extractor. On image recognition, the feature extractor is basically an identity function. It takes each pixel independently, maps it onto the color projected into red, green, and blue, and then feeds that to the machine learning algorithm. We have something much more difficult here because our feature extractor is highly nonlinear and features are non-independent. So how do we invert the feature extractor? So the first simple thing that you might try would be to take each feature, sort of come up with an inverse MFC function, and map each feature onto some audio, and then say, okay, good, I have this audio, merge the audio together, and everything works. And you could try that, and it wouldn't work. And the reason why it's not going to work is that if you remember that these frames are overlapping, so in particular, the second half of the first frame needs to be equal to the first half of the second frame, which in this case it's not. So if you try and merge, it will fail. And again, the second half of the second frame needs to be equal to the first half of the third frame, and it's not, so this will fail. And so when you actually try and merge these, what you're going to end up with is something that's not a valid reconstruction, and so the attack won't succeed. So instead what we're going to do is we're going to do this sort of one frame at a time. We're going to start with the first frame and do exactly the same thing, and just take the inverse MFC. Now what we're going to do is take the second half of this frame and fix it to be the first half of the second frame. And we're going to say that is fixed, you can't change it, leave it like that. Now given that, given the second feature vector, we're going to try and find an inverse and only change the second half of this second frame. And we do this with standard black box gradient descent, where we have fixed the first half of the frame, and we're going to try and target something so that when we run forwards through the MFC, we get something very close to the desired feature vector. So this gives us the second half of the second frame. Now, we're going to do the same thing again. We're going to copy the second half of the second frame down to the first half of the third frame and say, okay, that is fixed, you cannot change it. Given that, please find us a second half of this third frame that produces something which is very, very close to the next feature vector. We work our way through one frame at a time, going through in this way, until we end up with something which is a complete reconstruction. And now, merging everything becomes very easy, because we have ensured that each of the frames all line up. So, given that, it's actually not actually that easy. I've lied a little bit. All the details are in the paper, but there are a lot of things I can't really talk about today in the amount of time I have. But the one thing I want to call up in particular is that when playing these attacks, it only is an interesting attack if I can play it from a speaker and record it with a microphone and it still works. There is no useful threat model where I generate an attack on my computer and as an MP3 file and feed that directly into the machine learning algorithm. So we show that we can actually get around this by creating a model of the physical channel of what happens when you play it over the air. We use this model in our attack generation, and we even go a little bit further, and we actually play our attacks over the air during the generation. So this is sort of an online algorithm that plays attacks as it's going and improves the attacks to the point that they actually work when played over a speaker and then recorded with the microphone. So with that, let me get to a brief demo of what this actually sounds like. And with luck, everything will work. Okay, that sound hopefully loud enough. So, first attack, let's see what it sounds like. Okay, so that's the first attack. What was it saying? It was saying, okay, Google, take a picture. So if your phone was listening to this, so I should say this is the Whitebox attack. So this is not targeting the Google systems, but if the device, so we target CMU Sphinx. CMU Sphinx listening to this would hear, okay, Google, take a picture. Second demo. That one was, okay, Google, text 12345. And third one, this one was, okay, Google, browse to evil.com. Now, one interesting thing that you should note about how the human brain works is now that I told you what this is, it's okay, Google, browse to evil.com. I'm going to go back and play exactly that same thing again, and you're probably going to be able to sort of hear what it is that was said. So I'm going to play this demo one more time. So I played exactly the same sounds, but now that I've told you that, you can sort of hear what it was that was being saying. So we can actually change our attacks a little bit. So if we don't use the over-the-air playing phase, the attacks are substantially more difficult to understand. And so I'm going to tell you, this is again, exactly the same thing. Now that you know what it is, again, it's okay, Google, browse to evil.com. Let's see if you can hear what this one will be saying, which works only if you create as an MP3 file and does not work when played over the air. All right, that was it. So this attack works correctly when fed in as an MP3 file. Of course, it doesn't work when played over the air, but you can sort of think of this as the upper bound of what an attacker might be able to do if someone could improve our results of played over the air, someone who knows more about physics and the mechanics of a speaker work than I do. So something like that is sort of how difficult it could become. So there are some limitations here. The primary one is, again, that this is a Whitebox attack. So we're assuming complete knowledge of all of the model, which isn't really a realistic thing we can do. The other thing is that this attack actually, it turns out, doesn't work terribly well with background noise or echoes in a room, which is another unrealistic assumption. So the obvious question then is, can we resolve some of these problems? In other words, can we make this attack practical and remove the Whitebox attack assumption? So we do this, and we do this at the expense of a little bit of attack quality, so that the attack now is going to sound a little bit more easy to understand, but is actually going to be able to be applied to actual phones that people have. So how does the black box attack work? Well, since we don't have complete knowledge of the model, we can't start with the phrase we want it to hear and work our way with inverses, because we don't actually know how to compute the inverse. So instead what we're going to do is we're going to take an approach that's sort of like fuzzing. We're going to take some actual human saying some phrase we want it to hear as some input audio. We're going to feed this through something we're going to call an audio obfuscator. You can think of this sort of like something that makes random changes, and this will give us a candidate obfuscated command. We're going to test if this candidate obfuscated command works when applied to the actual speech recognition API and see what the phrase is that's outputted. If it's not the right phrase, then we just reject it and try another random modification. And if it is, then we keep it, and we'll listen to the ones that we actually generate at the very end and pick the one that's the most difficult for a human to understand. Now, the obvious question is, what do we do in this audio obfuscator? You can imagine that most changes will either make the command not recognized correctly or be too easy for a human to understand. So what we do is we split this, again, into two pieces, where we're going to use the fact that the MFC, the feature extraction function I introduced earlier, does a good job at extracting the important pieces of information out of the audio. So what we're going to do is we're going to take the input audio and feed it through the MFC to get some feature vectors, and then immediately invert it. So we're not really assuming that the speech recognition algorithm actually uses the MFC. We're just using this as a way to constrain our fuzzing approach. So the reason why this works is that since the MFC maps down to a much smaller dimensional space, there is necessarily a large number of inputs that the inverse can map onto. So by controlling the parameters used in the MFC and which inputs we map from the feature space onto the audio space, we can control how much noise we want to add. You can think of this sort of as fuzzing, but with the constraint that the initial phrase and the obfuscated command have the same MFC feature vectors. So this is how we do our black box attack. And so the evaluation for this, we can show actually works very well in practice. So what you're going to see here is you're going to see a phone sitting on the bottom of a table. This is sitting the closest to the camera, and the back of the table is sitting 10 feet away, some speakers. These are just relatively standard speakers. This is a standard office room. There's nothing special about those. And we're going to play some commands coming from those speakers, and we're going to see what the phone does.
Open adversary.com.
So if you didn't hear, it just said opening web page. And what it's doing is it's opening xkcd.com because that was the phrase that we told it to do. So even stronger, what we can do is we can show that this attack actually works with background noise. So here I've zoomed into the phone so that we can see what the phone is doing better. And additionally, what's going to happen is that this conference room has overhead speakers, and we're going to play from those overhead speakers some background noise to make this attack a little bit more difficult for us.
Google. Turn on airplane mode.
And this attack was turn on airplane mode, and so that is what the phone has gone and done. And one final demo. Again, same setup, this time still with background noise.
Google.
And again, you can hear the background noise. And we asked it to show facebook.com. And we're going to zoom out and show again, same setup, same speaker sitting 10 feet away with the phone on the table. OK. So brief comparison between the two. The Whitebox attack works on an open system, and the commands are heavily obfuscated. But the black box attack works on any system you could think of, but the attacks are slightly easier to understand. Both of these work when played correctly over the air. So we can actually play it coming from a speaker, recording from a microphone. But the white box attack doesn't tolerate background noise when the black box attack does. So all of this attack work leads to some obvious questions about defenses. So we do a relatively thorough study of defenses in our paper and break them down into three main categories. The first category of defense are defenses that simply notify the user an action was taken. So this can be something as simple as a beep, or maybe the phone saying exactly what it is that's going to do so that at least you're aware of what it is that was done. The second type of defense are defenses that challenge the user to perform some action. So you can think of this being something simple like, if you're sure you want to take this action, please touch the OK button on your phone. And this has obvious usability issues, but it would stop most of these attacks from working because it assumes physical access to the device. And the third type of defense are defenses which try and detect and prevent this from occurring. So you can think of these as defenses which are passive, running on the phone and trying to distinguish the difference between real human speech and actual attack commands. So one type of defense that we consider here is an audio filter which slightly degrades the quality of the input so that human speech still remains human speech but slightly degraded, and attack commands are now sufficiently degraded so that they no longer are recognized by the speech recognition. Another defense that I want to bring particular attention to are classification-based defenses. So we train a very simple linear machine learning model based on some standard features extracted from audio to distinguish the difference between valid commands and our attack commands. And this works with something like 99% accuracy. Now, even more importantly, what we can show is that we can train this classifier on the Whitebox attack and on human speech, and it will detect the black box attack. And similarly, we can train on black box attack and human speech, and it will detect the white box attack, despite that these are two very different attack approaches. So the machine learning algorithm is at least not trivially broken. And we're not going to try and claim that this is going to be the secure solution, but it's sort of an indication that something like this might work in the future. So with that, I'd like to conclude very briefly. Speech recognition brings many new possible attacks, and our hidden voice commands are something which are practical and work today. But the impact of these attacks is only going to increase as devices allow us to take more and more actions through the voice channel. We hope that future work will evaluate potential defenses, because this is a very interesting area where the attacks are not currently being widely deployed, so we have some time to construct some sound defenses which might actually be able to be deployed in devices. And with that, thank you for your attention, and I'll now take any questions.
Hi, Stefan Savage, UCSD. Really interesting work. I had a few questions, actually. So one was, I'm curious about the sensitivity of your work to compression, because the obvious mass delivery channel is like FM radio. And so I'm wondering if this works when you shove it through that kind of signal. But I'm going to ask the second question so I can get out of the way.
Sure.
Which is, I'm very interested in the potential application of this in a covert context, right? So if I hear that thing, I don't necessarily know what it is, but I know there's something weird that went on.
Sure.
And so what I'm wondering, if you've thought at all about exploring the extent to which you can hide these kinds of commands in something that, in fact, does not, in and of itself, sound suspicious. You know, the noise in music or something like that, but will be interpreted as speech by
Okay,
the systems.
Sure, yeah. So I'll answer the compression part first. So we haven't evaluated that thoroughly. I can tell you that in the Whitebox Attack command, the commands are recognized more heavily as speech than as me talking. So because we're able to invert the thing entirely, we're able to generate things which are like as good quality speech as you could want. And so I would imagine, I can't say for sure, that the attack would work. On the black box side, I think compression might help in the same way that an audio filter degrades the quality of everything, and that might help there. But again, I'm not really sure. My concern with compression is that compression sometimes, even if it's lossy compression, is sort of somewhat invertible, and we might be able to construct audio which, after uncompression, produces exactly what we want. For your other comment, so yes, these attacks sound somewhat weird, but if yesterday you were sitting and you hadn't heard this work, and you heard something like this and like you were sitting down enjoying your coffee, I don't think you would have thought it was an attack targeting your phone. I think you might have thought, oh, that's weird, and then immediately gone back to sort of enjoying your coffee.
That's fine, but now
yes.
I want to know if
now you know.
Or not.
Yeah, so now you know, is it possible, so the question, is it possible to like hide this in music? I think that would be a wonderful application. We weren't able to do that, but that doesn't mean it's impossible. I would imagine that it could be done. The reason why we couldn't do it for even the white box setting is that the MFC works basically over the over the frequency domain. And so when you're working over the frequency domain, there's only so much you can do. But it might still be possible to do this, but we weren't able to get it to work.
Hi, Zhang, Microsoft Research. Great work. So I don't know much about OK Google, but so other voice assistants, they use some like personalization. So they use some personal features. They do speaker identification, and then so the keyword detection, like Hey Cortana or Siri, those are, I guess, individual agnostic. But the comments, they try to use some personal voice features to personalize detections and so on. So that's that. Do you think that your attacks would be equally applicable to those?
So for devices which try and ask, like, is it my owner who's speaking? Right now, the only thing I'm aware of is some devices try and do pitch detection, in order, not as a defense, but mainly as a way so that
Yes.
two people in the same room don't accidentally control each other's
Yes.
devices. And so because it's not actually meant as a defense, I'm not sure that it's actually going to help here. I think that something like this could work in the future if you were able to have some kind of strong speaker detection. The one concern I would have is that speaker detection traditionally uses MFCC feature vectors, which are exactly what we've shown we can invert. So I'm not necessarily sure if it would be impossible to simultaneously invert the feature vectors of the speaker detection along with actually making it have the target phrase we want it to hear. I think that would be interesting work if someone could show that.
Okay, all right, thank you.
Algus Radice Google. I'm curious how robust your attack is against changes to the speech detection model on the server side. Do you have to retrain your attack each time Google or Apple or Microsoft pushes a new model on their side to detect voice, or does it work across releases?
I'm going to toss that to my co-author who can answer this question.
Yes, so the answer would be like, yes, we would have to retrain for the black box attack if the server-side speech recognition engine changes, because the way we generate our attack commands for the black box attack is we feed it to the current instance of the speech recognition system and get back the outputs. So if things change on the background, yes, we would have to retrain our attack. Thank you.
Hi, I'm Daniel Genkin from Tel Aviv and Technion. Have you tried hiding the voice that you produce up in frequency such that it's above the audible human range for humans but still picked up by the microphone?
Yeah.
And for the second question, have you tried using highly directional piezoelectric components that you can aim at a phone without anybody near just ever hearing whatever is being said? So this would allow you to hide it even more.
Can you repeat your second question?
There are highly directional speakers.
Okay, highly directional speakers.
Yeah,
okay.
and you can just aim it at the phone, and they're as accurate as laser pointers. And then nobody can hear, nobody's standing in front of, unless you're standing in front of the speaker, you can't even hear it.
Sure. So we haven't tried highly directionalized speakers. I don't know how they work. They may not work. For the first question on can we raise this into some like sound that humans can't hear? Unfortunately, no. The very first thing that most speech recognition algorithms do is have a bandpass filter, where they filter out everything below 80 hertz, which a human can produce, and everything above 4,000 hertz. Basically, keep only the things that the human voice can keep anyway.
Yeah, that was actually my exact question too. So if you use the Nyquist problem and you send frequencies if you're sampling at 44.1 kilohertz,
Okay.
If you have a better speaker and you can transmit a sound at 44 kilohertz plus or 2 times 44 kilohertz minus 4 kilohertz,
Okay.
the speaker will pick it up as a 4 kilohertz sound.
Yeah.
I see.
The microphone will pick it
Yeah,
up as a 4 kilohertz sound, but you won't be able to hear anything.
Yes, that might work. I would be concerned about making this actually work when played over a speaker and recorded by a microphone that wasn't high quality, because if the time samples weren't exactly when you wanted them to, and if you're playing at something 44 times 2 kilohertz,
You need a good speaker.
You need a really good.
yeah, you might need a really, really nice speaker, and also need to make sure that you don't control what the microphone is. The microphone is a cheap mic sitting on a phone.
That should be fine.
That should be fine.
Okay, so I'm not an audio engineer, but so if you say that this might be possible, it might be possible. I think that would be a nice thing to be able to show if someone could do that.
Thank you, Nicholas.